Hello everybody and welcome to this new lecture of Advanced Geodynamics, Theory and Modeling. Today's lecture plan is quite dense. We are going to start with some repetition, then we're going to discuss thermodynamic potentials, different forms of energy. Remember, we've already introduced internal energy and enthalpy. We get some more this week. Then we discuss thermodynamic identities. These are basically the Maxwell relationships. Then we will discuss about material properties, and we will finalize with a discussion on adiabatic heating. So just to refresh your memory, the total energy is the sum of all the energy in the system, both at the microscopic and macroscopic levels. So this means that the energy E, the total energy, is the sum of the internal energy plus macroscopic contribution of kinetic energy and potential energy, which may be gravitational potential or strain energy, elastic strain energy, which is stored. So this is really for systems which are in motion. Remember the example of the roller coaster where the conversion between potential and kinetic energy is taking place. That was 2 weeks ago. Just to stress it again, remember U, this is microscopic energy, and these ones are macroscopic contribution, means the scale of the whole system which is in motion. Remember the system. The system is defined by state variables. A system exists because it has a surrounding, and the boundary between the system and the surrounding is very important because this is where transfers may occur. Heat, mass, or exertion of work. The thermodynamic variables, they can be used to characterize or quantify the system. So we have the entropy, the pressure, the volume, and the temperature in this simple case. And now, energy can take several forms that will use different combinations of these thermodynamic variables. So let's start with internal energy. Again, just some repetition. Combination of microscopic kinetic energy of molecules and microscopic potential energy of molecular interactions. This is basically U. If we want to change U, we need to introduce the first law, du dt is q dot minus w dot. This defines the rate of internal energy. Now remember from the entropy, how we define the entropy rate, ds dt, q dot divided by t plus net production terms. If we don't have any net production term here, we can formulate q dot is t ds dt. So I'm just solving this equation for t. A second important term would be the work rate. Here I introduce a work rate which is linked to volumetric deformation. The work rate is the product of pressure times the rate of change of V bar. Let's introduce this into the above equation. So we substitute Q dot and we substitute W dot. We get an expression for the rate of change of internal energy, T ds dt minus P dV dt. This is an entropy rate. This is a volume rate. So what this shows you is that U, in fact, is a function of S and V. So it's a stated function that depends on entropy and volume. Now the enthalpy of last week, we defined it as H equal U plus PV. So this is the internal energy. This is the mechanical work potential. And we did a little bit of algebra last week, and we showed that the rate of change of H, this is the internal energy rate again, plus V dp dt plus P dv dt. But since the internal energy rate already includes P dv dt with a negative sign, these two cancels. So the dH dt is Q dot plus V dp dt. If you assume constant pressure, you cancel this term, and then you get dH dt, which basically shows you that at constant pressure, the heat added equals the change in enthalpy. Anyways, in the general case, dH dt is Q plus V dp dt. And if we substitute again Q par T ds dt, you get this expression here. dH dt is T ds dt plus V dp dt, which shows you that enthalpy is a state function that now involves the entropy and the pressure. So H is function of entropy and pressure. So these were two objects with which we worked already over the past few lectures. Question now is, are there any common energy expressions that we have not introduced yet? And the answer is, of course, yes. Let's introduce the Helmholtz energy. So the Helmholtz energy, F, is U, the internal energy, this time minus Ts. This is the energy not available for doing work. So it's the work that can be done by a system F at constant V and T. How to change F if we want to make the rate of H? Again, we end up having dF dt equals du dt plus d dt of Ts. You use the product rule, and we end up with minus T ds dt minus S dt dt. And we substitute the definition of internal energy, T ds dt minus P dv dt, such that dF dt will contain these four terms here. We have T ds dt and minus T ds dt that cancels out. So the rate of Helmholtz free energy ends up being minus P dv dt minus S dt dt. So what does this tell us now? It tells us that F is a function whose variables are V bar and T. So the Helmholtz free energy is a state function that depends on temperature and volume. So that's a new form of energy. Now, let's introduce again a new energy. This will be the Gibbs free energy. It will be defined as H minus Ts or U plus PV minus Ts. So the Gibbs free energy rate now will look like this. dG dt equals du dt plus d dt of PV minus d dt of Ts. So there we can apply the product rule to distribute the derivative over the product PV and the product Ts. We end up with all these terms. You see, this is coming from P dv dt and V dp dt. This is S dt dt plus T ds dt, with the minus sign being propagated here. And again, we have to remember the definition of internal energy, rate, which we will introduce at this location. Thanks to this, we will have the two terms, P dv dt and minus P dv dt, that will cancel out. What else do we see in this equation? T ds dt appears with opposing signs, so it will also cancel. So what does it tell us now? That the Gibbs energy is a function of temperature and pressure. So the rate is V dp dt minus S dt dt, oh, it's minus v dp dp. The Gibbs free energy is thus a state function that depends on pressure and temperature. So these are the explicit variables of G. The Gibbs energy is being employed a lot in earth sciences and, for example, in thermodynamic modeling, where, for example, one of the big applications is to construct phase diagrams. So you see here an example of phase diagram. There's a composition which is given. I think here is the composition of a sediment, so sedimentary rock, and now it's the equilibrium. So the Gibbs free energy is minimized for different values of P and T, and this allows to define the different region in this diagram where you have different paragenesis which are stable. So you see the different fields correspond to different paragenesis. So Gibbs energy is used to calculate this type of diagram, especially in the P and T space. Now, how did we achieve all these energy forms? In fact, there's a mathematical tool which is useful and which is called the Legendre transform. So here I take the example of starting from U, which is a function of S and V, and going to G, which is a function of T and P, to Gibbs. The point of Legendre transform is that you don't have to remember all the expressions of energy forms because you can recalculate it. You can find it again using this tool. So I quickly show you one example how to determine G knowing U. So what you need to know is the rate of U. So this is something we need to know, that du dt is T ds dt minus P dv dt. And now you want to derive G as a function of T and P. So now you know that you really want to create an expression in which you have the rate of temperature and the rate of pressure instead of having rate of entropy and rate of velocity. So let's start. What we're going to do now, we're starting with du dt, and we are going to use the derivative of the TS product. You know that if you make the derivative of the TS product, you will end up with S dt dt plus T ds dt. T ds dt is this guy here in U. So what about introducing T ds dt as being d dt ts minus s dt dt? So we can solve for T ds dt as a function of this and introduce it in this expression. This is what is done here. We replace T ds dt by d dt of ts minus s dt dt. By doing this is the first application of a Legendre transform. By doing this, we are introducing dt dt. So we are one step already of having a function which is a function which is already a function of temperature. So now we need to do the same for the pressure. So here we have the volume rate and we want to introduce the pressure rate. So we're going to do a Legendre transform for the product P. We are going to use the product rule of PV, which is P dv dt plus V dp dt. And we are going to substitute the expression of P dv dt by dPV minus V dp dt. Here it comes with a minus sign, so we end up with minus d dt PV plus V dp dt. This is the second application of the Legendre transform. By doing this, we've introduced the pressure rate and the temperature rate. So now we need to work out the expression. Let's take all the terms that have the time derivative and the product of variables to the left-hand side. We take them there, and we just use one time derivative for everyone. Remember, the derivative of the sum is the sum of derivatives. So we end up with d dt of u minus ts plus pv. This is equal to minus s dt dt plus v dp dt. This now, if you remember from the previous slide, is actually the definition of the Gibbs energy. U minus Ts plus PV. So the last step, we substitute G instead, and we get the expression for the rate of G as a function of the rate of T and the rate of pressure. We've built the Gibbs free energy, which is a function of T and P. So that's for the different energy forms. Second very important topic of this lecture here is the discussion about the Maxwell relationships. So the point here will be to set the equality between different partial derivatives of thermodynamic variables, or thermodynamic potentials actually. So it uses the energy defined in the previous slides, the different energy forms, so internal energy, Helmholtz, enthalpy, and Gibbs. And the aim will be to relate different partial derivatives together. For example, how entropy varies with volume at a constant temperature. This we will make it appear afterwards, but it will be equal to the variation of pressure versus temperature at a constant volume. So how pressure varies with temperature at constant volume. And why do we want to establish such kind of relationship? Is because some of the properties here, ds, dv at constant t, may be difficult to measure in the lab, while quantities like dp dt at constant volume is maybe much easier to measure in the laboratory. So how did we get there? What is this? Let's try to get to that slowly. As I told you before, to derive these relationships, you need to use the thermodynamic potentials. So here we will use the Helmholtz free energy. Here I'm not using a rate, I'm using a total differential. So you see a d, a straight d instead of a d dt. The same calculation rules apply between the rate and the differential. But for this type of derivation, it is more meaningful to work with total differentials rather than rate. So now we have df is minus p dv minus s dt. Let's have a look at that. What is actually minus s here? If you have a function like this, you should be able to identify that the coefficient which is in front of the differential of t, it's in fact the sensitivity of the function f with regard to temperature if you assume the volume constant. So if we cancel out this term, we will see that s is in fact df dt at constant volume. It's a slope in a way. So you need to be able to identify this from the definition of a total differential. You can get to this. So this is minus df dt at constant volume. And what is pressure here? pressure is in fact the partial derivative of F with regard to the volume, again with the minus sign because of this. So we have two partial derivatives of F that we can indeed identify from this differential form of the Helmholtz free energy. So df dv, df dt. We can derive once more. Let's do it. So if we derive once more this expression, we did it already with regard to the volume. Let's do it with regard to the second variable in this expression, which is the temperature. So we have d2f, dv constant temperature. We take the derivative of this with regard to T, constant volume. And this is, if we apply this derivative to that side of the equation, we need to apply it to the other side of the equation. This will be equal to dp dt. So we derive both sides now by with regard to temperature. So the second derivative comes from there, and the dp dt is because of this second derivation step. Let's do the same for this one. So here we add df dt. We're going at constant volume. We're going to derive it now with regard to the volume, but at constant t. So let's do that. We get the second derivative. d2f dv dt is equal to minus ds dv at constant t. And now we can use the Schwarz theorem, which states that the mixed derivative, second order mixed derivative of a function will be equal. So if we have d2f dt dv, it will be equal to d2f dv dt. That's the essence here. Because if we apply this theorem, then we also see that if the second derivatives are equal, it also implies that dp dt at constant volume is equal to ds dv at constant temperature. Remember, because they have this form. So if this is equal to this, it means that this part here is equal to that part. That's this. So now we came to the expression from which we wanted to derive this. This is a Maxwell relationship. Maxwell relationships, you can obtain them from each of the thermodynamic potential we discussed before. So if you use Helmholtz as a form of energy, you get directly dp dt at constant v is equal to ds dv at constant t. So you can always identify the coefficient here. We want to vary it with regard to this parameter, and this is done for this being constant. So dp dt at constant v. The second possibility is to build ds dv but at constant t. That's the Maxwell relationship you get from Helmholtz. If we look at the internal energy, we had du equal tds minus pdv. Again, I'm using a total differential. You can obtain dt dv at constant s will be equal to d or minus dp ds at constant volume. And so on. For enthalpy, we get dt dp at constant s equal to dv ds at constant t. And last but not least, Gibbs will give you ds dp at constant t is equal minus dv dt at constant p. So we have now built some relations between quantities that are not easily measurable. Now, can we do a little bit more, or can we identify some important material properties? That's what we do on this slide here. Remember, in the previous lecture, we discussed about heat capacity. And in the last lecture, we made a distinction between the heat capacity at constant volume and constant pressure. So in fact, the heat capacity at constant volume, we got it when we were looking at the rate of internal energy. If you assume the constant volume, then we get TdS. So this, in a way, means that the heat capacity at constant volume is the derivative of U relative to T. It's also the product of T times the derivative of S with regard to T at constant volume. The heat capacity at constant pressure was obtained from the enthalpy rate. Here it's written in a total differential form, but it's similar. Constant pressure, we cross out this term. So Cp is dH dt at constant pressure, or T ds dt at constant pressure. The expansivity is a material property that we have not been discussing so far. And this can be obtained, or it's related to the Gibbs energy differential. It takes the form of 1 over V times the variation of volume relative to the temperature at constant pressure. This appears in a Maxwell relationship. We come back to that later. And finally, we introduce the compressibility at constant temperature. We use the rate of Helmholtz for this. Constant temperature cancels out this term here. And what we get is that the compressibility at constant temperature will be minus V times dP dV at constant temperature. So there's a last parameter here to be introduced, is the beta, is the incompressibility, is nothing else than the inverse of kT. So since we've defined alpha and we've defined beta, I can now, for example, introduce an equation of state which describes how the density of the rock will vary with pressure and temperature. So what you see here is this expression. It's one out of many potential expressions for describing how the density evolves with pressure and temperature. This is a mistake here. I can correct it directly. You see rho 0 exponential beta p minus alpha t. It's basically how denser the rock becomes with pressure, and this is how lighter a rock becomes when temperature increases. Again, you see beta, it's the incompressibility factor, and alpha is the expansivity factor. Now you can create diagrams out of such expressions, and you get these nice diagrams here. For example, it shows you how density evolves with pressure for different types of rocks. Typical density is contained between 2,500 and 3,500, more or less. You see this almost linear increase with depth. So the larger the pressure, the denser the material. Here is the opposite effect. We have the minus sign here. If we increase the temperature, the density of continental material or mantle material will decrease with a given rate. And the rate is, of course, controlled by alpha or minus alpha. So this material property matters a lot when it comes to studying how the density evolves with pressure and temperature. Okay, now we go to the last topic of this lecture. The last topic is adiabatic heating. Adiabatic heating is a very important process in geodynamics. It's basically the heating or the cooling which is caused by compression or decompression of rocks. It matters a lot in gas and in the air. Also, you have adiabatic heating that matters. So think about a tectonic setting. You, for example, have here a subduction zone. In the subduction zone, the rocks are brought down to depth. The confining pressure increases. The material is thus compressed. This causes heating. So you have internal energy that rises because the molecules are getting closer to each other. In terms of rocks, it means that you increase the kinetic energy of lattice vibrations. This is going down, compressing the rocks, heating the rock. On the other path, if you're exhuming material or bringing material to the surface, you will decompress, and this causes cooling. So the internal energy decreases because molecules are getting further away from each other, and the kinetic energy of lattice vibration is decreasing. So how to quantify adiabatic heating? What we need to set as an assumption is that adiabatic heating is an isentropic process. So ds, the differential of entropy, will be equal to 0. We also need to recall the material properties and some of the Maxwell relation. Remember, earlier we've introduced Cp as Tds dt. Therefore, ds dt is Cp over T. We're going to use that. Now, I'm introducing the expansivity alpha again, 1 over V dV dt. And remember, we had the Maxwell relationship for Gibbs energy. This Maxwell relationship relates the rate or the derivative of entropy relative to pressure to the derivative of volume with regard to temperature. So from this, we can substitute dV dt is alpha V. So we can set ds dp is minus alpha V. So in the first slide, we got an expression for ds dt, and now we get an expression for ds dp. So if we make a total differential of S, we have ds is ds dt at constant p times dt plus ds dp at constant t times dp. But we have these two expressions for ds dt and ds dp, which we can substitute. So ds is Cp over T dt minus alpha V dP. We've stated before, we should consider an isentropic process. So we want to set ds is equal to 0. So let's set ds is equal to 0. We get Cp dt dt minus alpha V dP is equal to 0. So you can solve for dt dp. Let's do that. We've solved for dt dp. We get alpha V bar T divided by Cp. What is the definition of V? Remember, V was 1 over rho. V bar is 1 over rho. So we substitute V bar by 1 over rho, and we get dt dp is alpha T rho Cp. So at this stage, we get a variation of T relative to a variation of P. Now we're going to make another assumption. we want to estimate the variation with regard to the z coordinate, assuming a lithostatic loading, or just after actually. So let's use the chain rule. We have dt dp. dt dp by chain rule can be dt dz times dz dp. So we formulate this and substitute it in the expression. So dt dp, which is dt dz dz dp, is equal to alpha t rho cp. Let's solve for dt dz. So we bring the dp dz to the right hand side. We divide it by dz dp, which makes a multiplication by dp dz. So we end up with this cluster of values. And now we assume a lithostatic pressure gradient by saying that dp dz is rho g. So we replace dp dz by rho g. And now we even have rho at the top and bottom, which can cancel out. dt dz is alpha t g divided by cp. This is how to calculate a lithostatic adiabatic heating, so the dependence of temperature with depth in the mantle, using several basic material parameters such that the heat capacity at constant pressure, the thermal expansivity, and here we have gravity and temperature that also enters this expression. So that's more or less now the end of the lecture. It's also, we are reaching slowly the end of the thermodynamics part of this lecture of geodynamics. What we did here, we've introduced several forms of energy: the internal energy, enthalpy, Helmholtz, and Gibbs. We've introduced Maxwell relationships. We've discussed several material properties and how they relate to some of the Maxwell relationship. And using actually all this knowledge, we came up with a small derivation about how adiabatic heating works in the Earth interior. So thanks a lot for your attention, and see you in the lecture room.